Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, welcome to Lesson 13, Rotations. Classwork, Exploratory Challenge. You need a pair of scissors and a ruler. Okay, you will need to be cutting out an angle here. I won't be able to do that, obviously. I can't cut a piece of paper on my program, but I can copy this and manipulate it using the program. So I have a ruler, but I don't have scissors. So I copied this angle. This red angle is movable, and it is 75 degrees because it's right on top of the angle they gave us at 75 degrees. So it says line up one ray of the 75-degree angle with vertex A on the figure. Carefully measure the length from point P to A. So I'm going to take this and I'm going to rotate it, and I'm going to put this right here, but I need to get it so that it lines up. So what they're saying is take your angle that you cut out and do this. Okay, and then it says carefully measure the distance from P to A. Okay, so I really prefer metric system because there's no fractions. So I'm going to use the metric system here. So I flipped it over to metric. This is 6 centimeters, 7 centimeters, and there are 10 millimeters in between. So that is 68 millimeters. So I'm going to say over here, PA equals 68 millimeters. Okay. So then I'm going to rotate my ruler around like so and mark 68 millimeters, which is right at the end of this here, right there. And then I'm going to move my ruler, and this is going to be labeled A prime. So it says measure the same distance along the other ray of the reference angle and mark the location of your new point, A prime. Repeat these steps for each vertex of the figure, labeling the new vertex as you find them. Okay, so then I'm going to take my angle, rotate it so it lines up with B, like so. Okay, and I need to make this longer, so let's do this. Now keep in mind, I am making this larger. That is an enlargement or a dilation, or it will preserve angle measure, but not the length of the sides. So we're okay. It's still going to be 75 degrees. Okay, so then I move this to P like so, maybe a little bit shorter, like there. Okay, that looks about right there. Take my ruler, put 0 at the P, rotate it around. Now we are at 74 millimeters. So now I'm going to write that down, and that is PB. PB equals 74 millimeters. Now I'm going to rotate around the other side and mark 74 over here. And that is right here. Move my ruler, call that B prime. Get the idea? So now I'm going to bring this in so it's the same size, or it's going from P to C. And I don't have to make it any smaller, I guess. I could have left it. I just didn't, it wasn't long enough for it to reach B, so I can go beyond. That's fine, and I'm going to. So let's rotate this so it lines up. Rotate a little more. Okay, right about there. Take my ruler, put it on P, rotate it to C, and that is 42 millimeters. So I'll write that down so I don't forget. PC equals 42 millimeters. Rotate it around to my reference angle, like so, and mark 42 millimeters. 42 is right about there. Move my ruler. It's right here on the red line. Call that C prime. Okay. Now I'm going to rotate so it lines up with D. Like so. Put my ruler on 0, rotate it over to D, and that measures 61 millimeters. So PD equals 61 millimeters. Bring my ruler over to my reference angle ray the other side, and D is 61 millimeters, and I put a dot right about there. Move my ruler, call that D prime. Okay, keep going, rotate so it lines up with DE, move the vertex back to P, and let me see, how about right about there? A little less of an angle. There we go. Okay. Bring my ruler over, put it on P, rotate it, and that is 57.5, 58 millimeters. I'll just put 57 millimeters, and that is PE. PE is 57 millimeters. Go over to my reference angle, put a dot at 57. 57 is right here. Move my ruler. Okay, the dot is right there. That is E prime. Okay, and then I'm going to rotate so it lines up with F. Just like that. Put my ruler at 0. Rotate it. F is 22 millimeters. PF. PF equals 22 millimeters. Rotate to the other reference angle ray and put a dot at 22. 22 is right about there. Move my ruler, call that F prime. Okay, so now I move my ruler out of the way, I move my angle out of the way, and now, well actually I need my ruler. So first thing I'm going to draw is A prime, B prime. So now it says connect the 6 segments that form the sides of your rotated image. So I put that right here, rotate my ruler. And I'll use green. Okay, there's A prime, B prime. Now I want to go from B to C. Okay. I only put 0 at one of the points just because that's my reference of point of rotation of my ruler. You can just put the ruler anywhere on the paper. So there's B prime, C prime. And what I mean is you could just do it this way, but it's easier for me to rotate it to the correct angle if it's at 0. All right, so there's B prime, C prime. Now I want to go from C to D, so I want to go from C prime to D prime. So I rotate my ruler, put this at 0, rotate to D prime, which is right here, draw a segment up to D prime, and then bring my ruler to there, rotate it. We're going to E now. So this is D prime, E prime right here. And then we are going to go from E to F, or E prime to F prime. Okay. Like so. And now we want to go from F up to A. Okay, so there it is. That is A prime, B prime, C prime, D prime, E prime, F prime, rotated 75 degrees. Okay, page 2 brings us to this discussion. It says, in grade 8, we spent time developing and understanding what happens in the application of a rotation by participating in hands-on lessons. Now we can define rotation precisely. First, we need to talk about the direction of the rotation. If you stand up and spin in place, you can either spin to your left or spin to your right. This spin to your left or right can be rephrased using what we know about analog clocks. Spinning to your left is spinning in a counterclockwise position or direction, and spinning to your right is spinning in a clockwise direction. We need to have the same sort of notion for rotating figures in the plane. It turns out that there is a way to always choose a counterclockwise half plane for any ray. The counterclockwise half plane of ray CP is the half plane of line CP that lies to the left as you move along CP, ray CP, in the direction from C to P. Okay? The clockwise half plane is then the half plane that lies to the right as you move along CP, ray CP, in the direction from C to P. We use this idea to state the definition of rotation. Okay, so let's think about that a second. Okay, so here's a diagram I drew. Let this red line with the arrows at both ends be this line CP. Okay. Right there. Ray CP is blue. All right, so what does it say? It says the counterclockwise half plane of ray CP is the half plane of line CP that lies to the left as you move along ray CP in the direction from C to P. So this half plane going this way is the clockwise half plane. I'm sorry, is the counterclockwise half plane. So if I start here and rotate this way, I'm going counterclockwise. Okay? Then it says the counterclockwise half plane, blah, blah, blah. The clockwise half plane is then the half plane that lies to the right as you move along ray CP. So I'm going to take ray CP and rotate it. And I'll flip it around and put this point here, like so. Let me move it to the front so we can see it. Okay, and now this point here is P. So what they're saying is the clockwise half plane is then the half plane that lies to the right as you move along CP in the direction from C to P. Okay, so then we would go, what in the world? So then we would go, let me use a color I haven't used, orange. So clockwise would be, what is this doing? Clockwise would then be this way. As you go from C to the right to P, if you rotate this way, so P's rotating this way. This is clockwise, this is counterclockwise. So we use that idea to state the definition of rotation. For theta degrees, okay, so this is theta, it's called theta, T-H-E-T-A, it's a Greek letter, it's in the Greek alphabet, and it's right here. For theta to be greater than 0 but less than 180, that means it's positive but less than 180. The rotation of theta degrees around center C is transformation R, meaning rotation, C meaning center, of the angle theta of the plane defined as follows. For the center point C rotated around C theta degrees, C equals C. And for any other point P, R rotation C theta P is the point Q that lies counterclockwise half plane of C ray CP such that CQ equals CP and the measure of angle PCQ equals theta degrees. Okay, so let's talk this through. We have a point, and it is C. My pen's malfunctioning, so. Okay, so for the center point C, for any angle, so if I have a ray going out this way, then any point on this half plane, all the way up to 180 degrees, which is here, that would be straight line 180 degrees, then theta is positive. That is a positive rotation. Okay, for any theta between 0 and 180 degrees, the rotation of theta degrees around the center C is the transformation R C theta of the plane defined as follows. For the center point C, the rotation centered C theta degrees equals C. And for any other point P rotated around center C theta, P is the point Q that lies in the counterclockwise half plane of CP, such that CQ equals CP, and the measure of angle PCQ, so here's P, CQ equals theta degrees. So what they're saying is, if I drew the angle this way, okay, that is a negative angle, because we're rotating it clockwise, but it's also equal to theta degrees. So if this was 160 degrees and we go the other way, this would be 160 degrees, but it'd be in a negative direction. If that makes sense. Okay, so if we don't have that negative there, let's not go there, I suppose. They didn't want us to use the negative because they said it's equal. So this would be a 160 degree angle, and this would be a 160 degree angle, but it's just a rotation in the negative direction. It then says a rotation of 0 degrees around the center C is the identity transformation, i.e. for all points A in the plane, it is the rotation defined by the equation R, centered at C, rotated 0 of A equals A. Well, what do they mean by that? Well, if I have a point here at C, and A is here, and I rotate that 0 degrees, then A is still right there. That's all that says. Now it says a rotation of 180 degrees around the center C is the composition of two rotations of 90 degrees around the center C. It is also the transformation that maps every point P other than C to the other endpoint of the diameter of a circle with center C and radius CP. All right, so what they're saying here is if we have a circle, let's do it this way, and where's the center? Right here maybe. And so there's my ray. What's the center called? Center C, right here. A rotation of 180 degrees around the center C is the composition of two rotations of 90 degrees. So if I have a point that's right here, okay, and that's P. Well, CP is a radius. If I rotated this ray 90 degrees, it would be right here. And there would be my new P, or P prime. Okay? But it says a rotation of 180 degrees is a composition of two rotations of 90. So if I went 90 degrees this way, and then I did it again, I would be over here. And this would be P double prime, if you will. And that is another rotation of 90 degrees. Well, what's 90 plus 90? So what they're basically saying is this would be a complete rotation of 180 degrees. Okay. So it says it is also the transformation that maps every point P other than C to the other endpoint of the diameter of a circle with center C and radius CP. So what they're saying is if I rotated all of these and CP went here, then 90 degrees would be here and 180 would be over here. And you can do that infinitely many times just by rotating all of what I've drawn around this circle to different locations. It does not, P does not have to be at 0. P could be up here at 10 degrees, and then two rotations would be 190 degrees, and so on and so on. Okay, so a rotation leaves the center point C fixed. Rotating C theta degrees, C equals C. It states exactly that. The rotation function R with the center point C that moves everything else in the plane theta degrees, leaves only the center point itself unmoved. Any other point P in the plane moves the exact same degree arc along the circle defined by the center of rotation and the angle theta degrees. Then R centered at C theta degrees, P, the point P, is the point Q that lies in the counterclockwise half plane of ray CP, such that CQ equals CP, and such that the measure of angle PCQ equals theta degrees. We've already done that. Visually, you can imagine rotating the point P in a counterclockwise arc around a circle with center C and radius CP to find the point Q. All positive angle measures of theta assume a counterclockwise motion. Okay, let me rephrase that. All positive angle measures of theta are counterclockwise in motion. If citing a clockwise rotation, the answer should be labeled CW for counterclockwise. Okay, and that oftentimes confuses students. And the reason is, if we have a circle, okay, well, let me do it correctly. Let me do it right. If we have a circle, okay, and if I drew a coordinate plane, let me do that. Okay, so think of this as the coordinate plane, and this is the x-axis, and this is the y-axis. Okay, if I am going this way, that is a positive degree. Okay, if I am going this way, that is negative degrees. All right? And the reason is, if this is the point 0, 0, and we open it up, then our angle's going this way. So that is, we don't call that negative degrees. If that was a 40-degree rotation, then we'd say that is a 40-degree angle. We wouldn't say it's negative 40 degrees. All the way around to 180, and then you keep going around until it's 359 degrees here, and then back 360 degrees is equal to 0 degrees. So just keep in mind, as we go around, the angle that started here is opening up. So y is going positive first. Think of it that way. So if we're going up, y is positive, so therefore the angle is positive. If we're going down, y is getting negative at first, so it's a negative angle. Okay, a composition of two rotations applied to a point is the image obtained by applying the second rotation to the image of the first rotation of the point, which I've already done. I did that 90-degree rotation and then a second 90-degree rotation for a total of 180 degrees. So in mathematical notation, the image of a point A after a composition of two rotations of 90 degrees around the center can be described by the point R, rotation, of C, the point C, 90 degrees, or about the point C, 90 degrees, and then in parentheses, repeat it, R, C, 90 of A. The notation reads, apply rotation C, 90 degrees, to the point rotation center C, 90 degrees A, so that we lose nothing by defining rotation of about C, 180 of A to be that image. Then the rotation about C, 180 degrees at point A equals the rotation of about point C, 90 degrees, and then a rotation point C, 90 degrees of A again for all points A in the plane. Okay, page 3 continues with the discussion. So it says, in fact, we can generalize this idea to define a rotation by any positive degree for theta degrees greater than 180. A rotation of theta degrees around the center C is any composition of 3 or more rotations. Okay, so hang on. Okay, 3 or more rotations such that each rotation is less than or equal to 90 degrees. Rotation in whose angle measure sum is theta. For example, a rotation of 240 degrees is equal to the composition of 3 rotations by 80, because 80 times 3 is 240. Okay, so here's what they're saying. If I drew a ray, if you will, let's make it red, and it's 50 degrees, so it would be, like, here's 45. 50 would be about here. So this angle here let's say that's 50 degrees. Okay, so there's 50 degrees. So if I duplicate that and rotate it, then the sum would be 240 if we did it 4 times plus a 40-degree angle, for instance. All right, so let's do what they're saying. Example, rotation 240 degrees is equal to the composition of 3 rotations by 80. So let me move this out to 80 degrees. So there's an 80-degree angle right there. Okay, so this here is 80 degrees. So I copied it. So if I bring this over and rotate it and put it at the origin, so that it sits right on top of the other one, like so. 2 of them is now 80 times 2, or 160 degrees. Then I take this one and rotate it so that it rests right on this ray. So let me rotate it so it's that way, and then move it here. So what we just did was 80 degrees. 80 degrees. And we're going counterclockwise, 80 degrees. So this whole thing is 240 degrees. Okay, and we can do that with other angles as well, and they don't have to be equal. So here they said we could do 4 50-degree angles to add up to 200, and then another 40 degrees to add up to 240. But I just showed you what they're talking about with the 380-degree angles totaling 240. Okay, so it says, notice that we have been assuming that all rotations rotate in the counterclockwise direction. However, the inverse rotation, the rotation that undoes a given rotation, can be thought of as rotating in the clockwise direction. For example, rotate a point A by 30 degrees around another point C to get the image R rotated around C 30 degrees A. We can undo that rotation by rotating by 30 degrees in the clockwise direction around the same center C. Fortunately, we have an easy way to describe a rotation in the clockwise direction. Alright, so before I go any further, what they're saying is, let me draw a ray, and let me be accurate here. Bring the compass over, or the protractor over, put it right there. 30 degrees is right here. Okay, so there's a mark there, 30 degrees. So if I drew a ray from the center to here, this is a 30-degree angle. Right there. That is 30 degrees. So what they're basically saying in that last paragraph was, if I had a point here and I rotated it to this point here, that would be a rotation of 30 degrees. But if I took this point here, call it A, and moved it to this point, A prime, back, then that would be negative 30 degrees. Okay, and then they're going to say if all possible degree rotations are in the counterclockwise direction, then we can define a negative degree rotation as a rotation in the clockwise direction using the clockwise half plane instead of the counterclockwise half plane. Thus, a rotation centered at C, negative 30 degrees, is a 30-degree rotation in the clockwise direction. So let me do something here. Let me group these so that they rotate all together. Let me get rid of my ink marks. So what they're saying is if you rotated this like so about this center, like that, this is a 30-degree clockwise rotation. So rather than saying negative 30 degrees, it's a 30 degrees CW clockwise rotation. Since the composition of two rotations around the same center is just the sum of the degrees of each rotation, we see that the rotation around C, negative 30 degrees, of the rotation C, 30 degrees of A, is equal to the rotation of C, 0 degrees A. In other words, rotate it one way, rotate it back the same number of degrees, your start point is your finish point. The point never moved for all points A on this plane. Thus, we have defined how to perform a rotation of any number of degrees, positive or negative. Okay, continuing on. As this is our first foray into close work with rigid motion, we emphasize an important fact about rotations. Rotations are one kind of rigid motion or transformation of the plane, a function that assigns to each point P of the plane a unique point f of P that preserves lengths of segments and measures of angles. So rotations do not change shape or size. Recall that grade 8 investigations involved manipulatives that modeled rigid motions, example transparencies, because you could actually see that the figure was not altered. As far as length or angle was concerned, it is important to hold on to the idea while studying all of the rigid motion. Okay, so continuing on. Constructing rotations precisely can be challenging. Fortunately, computer software is readily available to help you create transformations easily. Geometry software such as Geogebra allows you to create planes, figures, and rotate them and give a given number of degrees around a specific center of rotation. The figures in the exercises were rotated using GeoGebra. Determine the angle and direction of the rotation that carries each pre-image onto its dashed line image. Assume both angles of rotation are positive. The center of rotation for exercise 1 is point D and for figure 2 is point E. Okay, so this is on your right page, I'm assuming, so I'm going to copy this onto the next page so we can refer to it. Okay, so here's page 4. I brought in a protractor. So what we're doing here is the figure in the exercise rotated using GeoGebra. So before I go there, let's go here. So GeoGebra is just simply geogebra.org. Or if you just Google GeoGebra, it comes up. And it is a really cool calculator, graphing calculator. And you can input all kinds of different shapes and rotate them, measure angles and all that. So they used GeoGebra to create these, is what they're saying. So that's a really interesting program that may help you if you are working on geometry constructions. Okay, so anyhow, determine the angle and direction of rotation that carries each pre-image onto its dashed line image. That's taking this, rotating it around to here, and it says assume both angles of rotation are positive. So we're working in the counterclockwise direction. So remember, there are 360 degrees in a circle. So I'm going to put my protractor right here. I'm going to rotate it so that I'm on A. Okay, A prime is right there. I'm going to rotate this over to A, which is right there. I'd say about there. And it's 75 degrees. Okay, see how it says it? I said it right there. So right here, 75 degrees. This 24 degrees is just from 0 up to A prime is 24 degrees. But if I click here, it is 75 degrees. You can see the markers. 10, 20, 30, 40, 50, 60, 75 degrees. So that is a 75 degree rotation. And why am I doing this? Because that's not the answer. It is 75 degrees from here to here. So we don't want to say that's a 75 degree rotation. If we're going from here this way, that is a clockwise rotation, and that would be negative rotation. And they said to assume that that's positive rotation. This would be negative 75 degrees. Okay? So think of it this way. If you went 75 degrees in the positive direction to get from A prime to A, then to get from A all the way around the same direction this way would be 360 minus 75. And 10 minus 5 is 5. 5 minus 15 minus 7 is 8. So that'd be 285 degrees. Okay, so (285 degrees), and you could say or 75 degrees clockwise or negative 75 degrees. Those are the three possible answers, but they said to assume angles of rotation are positive, so the answer is 285 degrees. Okay, in this diagram, it says that we're rotating A, B, C, D to A prime, B prime, C prime, D prime. So to get from here to here, our center of rotation is E. So it says, did you draw angle DED prime? So I'm going to do that, because I did not. So if I draw a segment, and let's use, I don't know, red. angle DED prime. So D to E to E to D prime. So there is my angle. Okay. So that's our angle of rotation. So I'm going to rotate my protractor around, put the crosshairs right on E, like so. Rotate, oh, that's sizing. Rotate so that I'm on D, and then use my tool here to find the angle measure. And there it is. So it is from here 0. So we're going from D to D prime, which is from 0 this way. It is 10, 20, 30, 40, 50, and it looks like 51 degrees. Is that right? 40, 50. Okay, so I'm seeing 51 degrees. Here's my rotator. So here is 0. 1, 2, 3, blah, 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 blah. Oh, I'm sorry. It is, yeah, right there, 50 degrees. Okay, so the rotation is 50 degrees, or 300, wow, why am I way over there? My pen's disappeared on me during this, and I don't want to reboot, so I just have to keep going up here. Or negative 310 degrees, or 50 degrees clockwise, which is a negative 310 degrees counterclockwise. Okay? Or clockwise, I'm sorry, clockwise. So negative 310 is clockwise, and 50 degrees is clockwise, but our 50 degrees is actually counterclockwise. So they did say to assume that it was positive, so let's just say 50 degrees. Now can you find the angle of rotation? Let's move on to find the center of rotation, follow the directions. Okay, so I've already done this. Okay, so the answer was 50 degrees. Okay, page 5 brings us to another example. In this example, though, they are not even giving us a point of rotation. We do not know where the center is. So A says, draw a segment connecting points A and A prime. So I'm going to do that. Let's use red. So here is A, and there is A prime. Okay? Using a compass and a straight edge, find the perpendicular bisector of this segment. So I get my compass. Oops. My compass. Let's just move it over here. And a ruler. Find the perpendicular bisector of the segment. Do you remember how to do that? So let's change the color of my compass to green. And what you do is you put the compass on one of the ends, open it more than halfway, rotate it around, okay? And I'll open it even more because it's not clear that it's more than half. So there it is, more than halfway. I'm going to draw a circle, and then I'm going to move my compass to the other end, located at point A prime, and draw a circle, like so. Okay, so I'm done with that. Bring my straight edge over and draw a segment from intersection point to intersection point, like so. Okay, so there is our perpendicular bisector. so let's get rid of the circles now. There's my perpendicular bisector, so this is 90 degrees. Draw a segment connecting points B and B prime. Okay, so let's do that. I'll use green this time. No, I already used green. Blue. So here is B. Here is B prime. There's our segment. Find the perpendicular bisector of this segment. Okay? So, get my compass back on the screen. Stand it up straight. Put it at B. Right there. Rotate it around. I'm going to close it just a little, as long as I'm more than halfway. Draw a circle. Okay. Move it to the other end. Draw a circle. And I'll put this right at 0, as close as I can. Rotate it to the other segment. So as you can see, I'm going to connect my circle bisectors, or where the circles intersect, I should say. They aren't bisecting the circle. And that's where my circles intersect. Okay, let's get rid of those marks from my circle. Okay, so there's the perpendicular bisector of the blue segment, BB prime. And this is the perpendicular bisector of AA prime. The point of intersection of the two perpendicular bisectors is the center of rotation. Label that P. Okay, so I'm going to make it black, put a dot right here, and label it P. All right. Justify your construction by measuring angle APA prime and BPB prime. Do you get the same measures? Okay. So I get my compass, my protractor, and I want to measure angle A, P, A prime. So I'm going to delete my bisectors now, and I'm going to draw an angle in purple from A to P to A prime. Okay, and I want to measure that angle. So I put my compass at P. As close as possible. Put those crosshairs, I said compass again, it's a protractor. And put it on P like so. Rotate it so we're at 0. Bring our marker up and it will tell us how many degrees that is. And we're working this way. We're going this direction, which is counterclockwise. So really I should have my protractor with the 0 on my original point A, not my A prime. So let me do this correctly. Right there. And then move this to here. It looks like it's from here, we're going to count inside. That looks like 82 degrees. Okay, so I'm going to say the measure of angle AP A prime equals 82 degrees. Now we're going to move the protractor. Do the same with B. So I want to draw a segment from B to P. So I'll just use the same lines and move it over here. Okay, and move this to B. Like so. Now I'm going to measure this angle. So I'm going to put the crosshairs right on P. Move this so that that line, that 0 line is right going to be like right there. And as you can see, I don't have to move this. They are the same. That is again 82 degrees using the inside. Okay? So the measure of angle B, P, B prime is also 82 degrees. Okay, so in this exercise, now if I get rid of this and get rid of this and get rid of all these, we found the point of rotation by doing perpendicular bisectors of two segments, A to A prime, B to B prime, and then measured that angle, and they were equal. Okay, page 6 is two exercises, 4 and 5. Find the centers of rotation and angles of rotation for exercises 4 and 5. So you need to do what we just did and find the center of rotation. So pause the video, see if you can do these on your own, and then unpause, and then we'll see if you did it correctly. Now keep in mind we have A, B, C, 3, 4, 5, 6 points, which means we have to draw two perpendicular bisectors of segments that go from A to A prime, for instance, or we could do B to B prime, C to C prime, D to D prime, E to E prime, or F to F prime. So there are multiple solutions to this. We need to do two, so it could be A and B, or A and C, and A and D. You get the idea, right? So what I'm going to do is I'm going to choose the further of the two, because that, I believe, would make it more accurate. So I'm going to go furthest out. So I'm going to do C prime to C for one of them. And I'm going to do, oh, I don't know, how about E to E prime, like so. So there's my two segments I'm going to choose. Okay, I just chose two. I didn't want them to cross over and so on. It doesn't matter because I could erase them after I'm done. But now I need my compass, and it's, oops, it's set to purple, which is fine. So the only problem with this program though is I need to open this up at least halfway. So let's move this down, put this right on the end C right there, open it more than halfway, and draw a circle. Move it over to C prime, draw a circle. Get a ruler and draw a segment from intersection of circle to intersection of circle, like so. And I will do it in green so you just can see the difference in colors. Okay, so there's one perpendicular bisector. So I know the point of rotation is somewhere on this segment. Okay, but there's still infinite locations where it could be. I'm going to delete these circles just so it's not cluttered. I'm going to move to E. I will shorten this a little bit, draw a circle. Actually, undo that. Let's make this purple. Draw a circle. Move it to E prime. Draw a circle. Get my ruler. Put it right on that intersection of the two purple circles, intersection of the two purple circles. I'm going to move it down a little bit, and it looks like it's okay, just move. So let me see, right there. So if I draw that segment, but I want it green. Which green did they use? That one. All right, so there they are. There are my two perpendicular bisectors. So I can get rid of the circles. Now I found my point of intersection, so I'm going to label that right here, and that is my P. Let's erase all this just to get it out of the way. Okay, so now I have my protractor, and I'm going to draw two segments again. And this time I'm going to go closer. So I'm going to draw a segment from A to P and P to A prime. there is my angle of rotation. I'm just going to do the 1 because we just proved in the last one that they're the same no matter which point you choose. So if you chose F, it'd be to F prime. So FP, F prime. So then I'm going to put my compass on P, rotate it so that the 0 is on A. Remember, you want to put that on the pre-image point because then when I rotate this around, we want it positive degrees. So if we come all the way around, there's 180. I can't go any further, or can I? This compass goes all the way around in a full circle, or protractor, I mean. So now that it's on 360, I see that my center was off a little. So let's put it right at center and rotate it so that it's right on A for 0 degrees. So it's going through A, and now I'm going to rotate that around to A prime, which is right here, I would say right there. And that is 100 and, no, it's not 154 degrees, just kidding. If this is 0, we have to use the inside here, and we're all the way up to 242 degrees. So number 4, I would say, was a rotation around P, comma, 240 degrees. And I rotated A, so I would say A. Okay, so the next one, let's just move this off to the side here. Again, I'm going to choose the furthest. Okay, and notice I'm using this tool, by the way, so you would have to use a ruler if you're doing this on paper. So I'm going to draw a segment from, let's see, the furthest away, maybe E and E prime, like so, and I don't know, how about D and D prime? I just don't like choosing ones that intersect, that cross. So there we go. Now we're going to do a perpendicular bisector to both lines segments, I should say. Make sure your compass is open more than a half. Let's do it in blue. So there's one circle. Move this to the other side to E prime. Draw a circle. And then grab my ruler, put that on 0, rotate like so, and I'll draw a green line segment for the perpendicular bisector. So there's the perpendicular bisector of E prime. Alright, so now I'm going to erase these circles. And repeat on D prime. Circle. Move over to D prime. Circle. And I'm done with my compass. Now I'm going to draw a perpendicular bisector. Let's use purple this time so we see the difference of the two. Put that right at 0, rotate. And it looks like right about there. Okay, those 2 points intersect. We'll call it point P, which is right here. Okay, so let's clean this up a little bit. I don't need my circles anymore. Oops, deleted the background. Don't need the circle anymore. And I don't need this or, wow, hello. This, I don't need this, I don't need this, and that was a mistake. Okay, so there's P. This is point P. That is my point of rotation. So now I am going to draw a segment. And remember, since I have a program that draws straight segments, I don't need the straight edge, but you do. So if I start it at C and go to P, and start at P and go to C, like so, then I measure that. Let me make this a little bit more accurate. Like so. And I measure that. So you put your protractor center at P. You rotate the protractor so that your 0 is on the pre-image point. C is right there. Let's just move it a little bit more. How about right there? And then I bring this around. So here's 0 degrees. It's rotating counterclockwise, which is positive degrees, until I get to C here, and it was 92 degrees. So let's use notice how I did this. R tells us it's a rotation. This tells us where it's being rotated, center, P, comma, the degrees was 92, and the point was, I use C. So this says a rotation about center P, 92 degrees, C. And that equals C prime. Okay? Okay, page 7 brings us to the end of lesson 13. Review the lesson summary and go to your problem set.